Welcome to the Math Record. Today we'll be covering the one proportion z-test and its confidence interval. This video will cover part 1 of chapter 2 in our statistics class. Okay, let's begin. The one proportion z-test is basically just going to be a sampling distribution where you're going to be working with just one proportion. This is usually the most simplest case and the one that you're most likely going to use other than like the t intervals. So a one proportion z-test, right? The first thing you should ever do when you're doing a one proportion z-test is that you have to check conditions. So the first thing you have to do is to check conditions. Okay, for conditions, you have to say that the it's random. Just write this out. Random. Okay. Conditions. So for random, so the sample uh is random. Basically, you basically just have to write this down. So usually when they ever ask these questions, yes, if you're making a one proportion z-test, you had to get a random sample. So you had to go out to like a random to a random population and gather like people randomly do like a simple sample like a SRS, the simple random sample, like stratified or clustered, as we explained in chapter 1 in our statistics class. And then you had to say that the data is independent, which basically that the individuals are independent of each other. So individuals are independent. Depend. I'm not gonna write the entire thing, but basically, it states that like just because one person chose one like option doesn't mean the next person is gonna have a higher chance of or a lower chance of choosing that option again. So if you choose red, like you choose red, just because you choose red doesn't mean your friend will choose red. You know, so that's basically independence. So each person is not affected by each other. And then there is the 10% condition. So, which basically states that your sample size is less than 10% of the entire population of which you're measuring. So, let's say you're taking 10 students. No, let's say like 50 students from a high school. You have to say that that 50 is less than like 10% of the entire high school. So let's say like your 50 is 10%, then there's at more than 500 students in your high school, basically. So it has to be less than 10% of that condition. And last thing we have, let's kind of delete this because we need room, is that sample size. Okay. For sample size, it just states that NP, the null NP, is greater than or equal to 10%, and the NP and QO is also greater than or equal to 10. So N is the sample size, P is the probability that you want to like calculate, and Q is the opposite of that. That's not it. So basically, an example would be like let's say uh, you choose a random survey and it's from a high school and you want to see if they are a freshman, right? So you want to see if, let's say your PO from your the PO that you think it's true, it's not from the sample but you think it's true. That's since there's like you think there's an equal amount of freshmen, sophomore, junior, and seniors. You think that it's 25%. So your PO is 25%. That the probability that you think it's freshman, you want to measure as freshman, and then QO is going to be QO subscript O, which is going to be opposite of that. So it just be 1 minus 0.2 is 0.75. The 0.75 stands in context, basically means uh the probability of a student that you think that is not a freshman, because the probability of a freshman is 25%. So the probability that's not a freshman is 75%. So then you multiply those and then you have n, which is from your sample, multiply that 25%. So you have like, let's say you have like 20 people from your sample, and 20 times the 25% would be equal to 5, which is not greater than 10. So you need a higher sample size. So that's basically what this means. So yeah, if you had so for a one proportion z test, you have to have basically all these conditions checked. If you have like one, usually random independent is already checked and 10% condition because you can't always tell. Sample size is the one that you always want to do because sample size you have to prove this mathematically. So that's the one that you always have to do the math on. For the random, the independent, and the 10% condition, you could basically just write it down and say it's random. You could say it's independent, and you could say it's less than 10%, basically. So for sample size is the one that you always have to check, the annoying one. So that's the first thing you have to do. You have to check for conditions. After that, once you check for conditions and you say you could use the test, you have to write it out. So you have to write the transition statement, which basically is that you could basically just write this. Since the conditions, sorry, my handwriting is bad. Conditions are met. Um, I can construct a one proportion the test. So that's basically all you have to write. You just have to say that your conditions are met, and you have to say what test you're going to be using. Because they don't know what test you're going to be using, because maybe you're using a two proportion. So whenever you're taking like exams like the AP exam, you have to write this out. So that's the second thing you have to do. The third thing you have to do is now you're going to be doing the test, is that you have to write down your hypotheses. So basically, your null hypothesis is H subscript O, and your alternative is H subscript A, because alternative A, null, 0. So your null hypothesis would be like if your p-value is equal to your PO, which is what you think is true, or if your p-value is like kind of different. There's only three cases. It's either the p-value is greater than PO, the p-value is less than the PO, or the p-value is not equal to PO. So basically, what's asking would be like if it's actually if what you think is true, the actual p-value. So let's say it's actually not 25% for the freshmen, and it's actually like 33%. So p is like greater than po, but you don't know that, so you have to use these hypothesis tests. So you're gonna either say like the question is really explicit about this. Usually when they ask, they usually ask, let's say you think it's 25%, but then based on your sample, it shows that it's greater than it. So you want to think, so you think it's greater than PO. So then based on your sample, you logically think it's greater than PO. So you write P is greater than PO. So you have like, let's say you have 100 students and you took 33, right? So you have 33% for freshmen. Um, and then you say P is greater than PO because 33% is greater than 25%. So you're gonna test the hypothesis, and that's what you're gonna be doing. And you gotta test if it's true or not, if it's unusual, because that's what tests are for, to test if it's unusual. So that's what you're gonna have. You're gonna have either P is greater than, less than, or not equal to PO. Um, Usually greater than and less than is pretty similar. Usually when you're making a norm model, let's say a norm model, right? So if it's greater than something, it's just right here. If it's less than something, it's right here, right? It's basically just a line, and then whatever's less than is just less than it. It's less than that, like less than the values of that line. What's greater than line is less than that. Or then if it's a two, if it's not equal to, it's a little strange. So it's gonna be like if you have a line right here, then it's not this, or you have a line right here, which is right here. So this will be equal amount. So the distance away is here. So let's say this is 2 standard deviations away negative, then this is 2 standard deviations away positive. You have to calculate these areas. Since it's symmetric, the areas is basically the same. So whatever you find for the area here, just multiply by 2. Or you have an area here, then you just multiply by 2. So you could do either or, depending on which one you have, like as your number. Because if you have, which we're gonna explain later on in which we could explain later on in the sample, in an example. So that's the third thing you're gonna be writing. your your tests, your null hypothesis, and your alternative hypothesis. So the null and the alternative, and then you can spell hypothesis. The hypothesis, basically. You write that down here. I'm not gonna write it again, but basically, that's what you have to write. Because that's what you're always gonna write for the hypothesis. Is P is equal to the no one that you think that you claim is true. Then you write the alternative, what you think it might be right, or what the question claims to be right. So that's the third thing you gotta do. So conditions, transition statement, then write your test. The next thing you all want to write is you have to define your variables. Sometimes you don't have to do this, but usually I do because you want to know what you're going to be using and you want to get confused like what variables you're going to be using. So PO is the proportion, because you're working with the z-test, proportion claimed to be true. So what the like usually when you're answering questions like this is like let's say a company claims it's 25% of its product is like this color or something, then basically it's 25% is claimed to be true. And then you can have something which kind of looks like like a little part of a triangle, but not entirely. This is called p hat, which is gonna be proportion from your sample. So basically, let's say a company like some kind of chocolate company says that 25% is red, right? There's their claim, so that's gonna be your PO. So that's gonna be your PO right here. So this slate is like R or 25%. And based on your sample, which you took out of 100, right? You get 33 red. So your P hat is going to be 33%. It's basically just that. So for your red. And then from there, you could get like your Q hat, but you're not, which basically is like the proportion from a sample that's not that number. So if this is 33 over 100, then it's just 100 minus that 33, which is 67 over 100. It's all P. Whatever the P value is, it's just 1 minus that P value to get the Q value. So you want QO, which proportion that is like not, that's claimed to be not red. Because if 25% is claimed to be like red, then 75% is claimed to not be red. So you just use a little bit of logic instead of just subtract it. Okay. And then usually you just need to find the PO, which is the proportion claimed to be true, the P hat, and the N, which you always have to write as the sample size. But you have to write it in context. You have to write all these in context. So you can't just say proportion claimed to be true. Claimed to be true of what? You know. So proportion of red chocolate claimed to be came to be like inside the box, you know, or like, and then your p hat could be like proportion of red from your bag of chocolate, and sample size is like your the amount of chocolates you have in your sample of in your bag in your sample which is the bag basically. So you have to put everything in context. Because you don't want to be vague. You want to be as precise as possible, and you want to explain everything as clearly as possible. So that's the fourth thing you want to do. Define your variables. The fifth thing, you might not also need to do this also. This is the mechanics, which basically do all the math. But also your calculator could also do all the math. But if you want to just write down the numbers, you could. So your mean, like basically when this is like with the model, like when you have to draw the picture and everything for the mechanics, you have to you have a mean. Your mean is just gonna be equal to your PO. Okay? And then you have something called your standard deviation again, which is going to be equal to square root of your PO times your QO divided by your sample size. Sorry, I have you write the entire thing. It's going to be square root of the entire thing. Let me just rewrite this. Square root of PO times QO divided by N. Okay? So you basically square root the entire thing. So this is, you're just going to calculate it because this is just going to be the math portion. and then your z-score, right? It's gonna be equal to your p hat minus your PO divided by your standard deviation. Okay, so basically it's just your p hat, your sample, minus the mean divided by the standard deviation, and that's the general idea. It's always just the usualness of your sample minus the mean divided by the standard deviation. And then you're gonna have something else. It kind of looks like a fish that I always think about. It's called the alpha level. So it's the percent. Basically, the alpha level is the percent amount that you like that if it's like under it, then you're gonna say it's unusual. Usually, the alpha level you're always gonna use is just 0.5. But sometimes questions might say the alpha level is like 0.1. So if it's like less than like 5%, then basically you're gonna say it's unusual because like you expect anything like in 95% of that data to be like not that unusual. But if it's like less than that, like basically 5%, like outside that range, then you're gonna say it's unusual because it's so small that you think the chances are too small for it to occur. So that's why you say it's unusual. But you're not 100% certain. Stats you're never 100% certain. But when you have the alpha level, you usually just write 0.05 or whatever the alpha level they give you. And then the last thing you want to do for the mechanics section is that you want to draw a picture. And you want to label everything, basically. So you have a picture, you have a Z model, so you're trying to draw a bell curve. And then you write the mean, so the mean is right here, so you just write PO, because the mean is equal to PO. And then you write basically, and then you don't have to write ticks for every single standard deviation. Usually you just write the standard deviation right here. So you just write the number for the standard deviation right here. And then you basically, whatever you get for your proportion for p hat, your p hat. If let's say your p hat's right here, right? Your p hat, then just write your p hat right here, and then say if the area is like greater than if you say the no hypothesis is p is greater than po, then you're just gonna write is greater than it. If it's p is less than po, then you just say it's right here, basically, right? So right here. Or if it's not equal to, then you have p hat, and then you have negative p hat, basically, and then you basically right here. Z-score, as I said in like chapter 1 part 5, which is basically a number which you're just gonna plug it in to get the ants the area under the curve. So basically your p-value will be equal. You're gonna be using a calculator for this anyways, for the p-value. Like the mean, the standard deviation, and the z-score you could do all by hand, but basically the p-value you're gonna be using a calculator. Basically all the time, unless you want to use calculus, which I'm not going to teach. So we have a p-value, which is basically just the p where z is greater than whatever the number you got. So whatever you got as your z-score, right? So if you have a z-score of 1, then you say the p where your z-score is greater than 1, and you basically just plug it in. For the n-spire though, usually I don't think you have to write the z-score. I think you usually just write the p hat and you just get the answer. But when we get to it, we'll get to it. I'll show an example at the end to show you how to do it. So once you make a picture, I don't know, I erased it. So basically, that's what you do. You write the p-value, you write the mechanics, the mean, the standard deviation, the z-score, write your alpha level, so then they know what you're comparing it to, a p-value and no model. So let's say like this is like 2%, right? Then it's less than your alpha level. That means it's really unusual. So if right here instead of 2% we say it's like 7%, right? We say it's 7%. Then when we say it's not really that unusual, because that's the number you choose. For stats, it's kind of like all willy nilly, and they just kind of give you like some kind of random number. So the alpha level 5% usually the case. Okay. And the last thing you're gonna do is that you're gonna write a conclusion. There's see, so basically the general idea is like based on the p-value. all right? But you have to compare it to something. So the p-value of whatever your number is, which is something like compared to, so it's either like less than or greater than the alpha level of 0.05, then you have to write something. So basically, you basically just write the statement. So based on my p-value of, like, let's say 0.02, which is less than the alpha level of 0.05, then basically that's what you're gonna do. So okay. So when you write the conclusion, basically what you have is that if your p-value is less than 0.05, you're gonna say I reject the null hypothesis. Because you're saying, basically, since the p-value, let's say, is 0.2, is less than 0.5, right? Since it's so unusual, you have to reject the null hypothesis. Because they say that they claim that the p-value is equal, the p is equal to the po. So they claim it's, let's say, in a case was 25%, when it really isn't when we use that 33. So I'm not sure if 33 is unusual, but let's say it was. So if the 33 was unusual, then we say we reject the null hypothesis because the sample tells us that, like, maybe they are wrong. So we say the null hypothesis is wrong. Null hypothesis is wrong. So the p is not equal to the po. So and then after you write this, you have to talk about the alternative. Because every single time you write a conclusion, the first sentence you write is that you either reject or you don't reject the null hypothesis. And then you follow it up with talking about the alternative hypothesis. So if you reject it, that means you say the alternative hypothesis is right. So you say there is, you can't say there you are certain that the whole hypothesis is right. You say there is evidence um to suggest, because you want to be like because you're never 100% sure, there is evidence to suggest the alternative hypothesis. I'm just gonna write HYP. I'm not gonna write the entire thing. Is true. Where's my cursor? Is true. Okay. But you always have to put this in context. So you can't just say you can always just say I reject no hypothesis. That's always like the first sentence, or like you fail to reject no hypothesis. But the second one, you always have to, like, write it in context. So you can't just say you suggest the alternative hypothesis is true. You have to say, like, uh there is evidence to suggest that the the amount of freshmen is greater than 25%. You gotta write it in context. That the null hypothesis is true, that the freshmen are greater than 25% of, like, the incoming freshmen are greater than 25%. I mean, the total amount of students is greater than the total amount of freshmen is greater than 25% of the amount of students. That's what you have to write. But that's only for, like, when p-value is, like, less than 0.05. If you have it say it's greater than 0.05, so it's within that data range, you say I fail to reject the no hypothesis. I'll just write HO. You have to write no hypothesis. You can't just write HO. So you have to write those in words. So you have to say I fail to reject the no hypothesis because it's less than thing. Because you have to write the first sentence first, based on a p-value of, let's say, point 1, which is greater than the p-value of 0.05. I fail to reject the null hypothesis, because the 0.10 is, like, greater than 0.5. Because you say that if it's less than 0.5, then basically it's going to be outside the data range, and it seems really unusual because only 2% of it will work when you expect it to be, like, at least 5% or greater that works. So if it's 5% or greater, then you're not gonna think it's that unusual. So I fail to reject the null hypothesis. And then you write there lack, because you're never 100% sure, there lack evidence to suggest the alternative hypothesis algebra HA is true, and which you also write in context. So in our example with like the freshmen, it would be like since with a p-value of 0.1, which is greater than the alpha level of 0.05, I failed to reject the null hypothesis. There is evidence to suggest the alternative hypothesis, which is that there is that the that more than 25% of the students are freshmen is true. So there's lack evidence to suggest that like 25% of the freshmen, 25% of the students are freshmen is true. So so we're not saying there's no evidence of it. We're just saying there lack evidence. So we're not 100% sure, but we're saying like there isn't enough evidence to say that it's that unusual. And that's what we're writing all the time. We're always unsure. We're basically just always unsure. And that's basically what you write for like the hypothesis test. And then if they ever ask you to follow up with a confidence interval, a confidence interval will tell you like where the data is generally located at, like around the mean, like what amount of range it is. But so it could be outside the range. It's gonna be unusual, but it's gonna be outside. So to do this, you just have to find the mean. The mean is equal to your p hat this time. And now your instead of using standard deviation, we're gonna be using something called standard error. It's basically the same thing. They just reworded it. Standard deviation is for like an actual number. Standard error is for when you're using a sample. So standard deviation, like when you're really when you know for sure that's the answer. So when you're claiming is to be true when you're using PO, which you're using standard deviation for PO, it's claimed to be true, so you think that's true. So you think that's for standard deviation. But for standard error, you're using your populate. You're using your sample. Then your standard error, which I write as SE, is basically equal to the square root of p hat times q hat divided by n, which is the same thing because like standard deviation is just basically the square root of PO times QO divided by n, as I stated before in the video in like a few minutes back. But basically, they're basically the same thing. It's just standard errors for the sample now when you're using p hat because that's from your sample. So like our PO would be like 0.25 times 0.75. Let's say we have a sample of like 100 students. Yeah, we have a sample of 100, which is square root, and that's your standard deviation. But now our standard error, which basically just be the square root, we say we have 33 students out of the 100 that have like are basically freshmen, so we have 33 out of 100 times 67 because it's 1 minus q hat. Q is always just basically just 1 minus p, so it's just be 1 minus 33 or 100 minus 33 is 67 100. Right? So when you add 33 over 100 plus 67 over 100 is equal to 1. So you multiply 33 over 100 times 67 over 100 divided by the sample size, which is 100. Because these are always proportions. You know, you're not going to write 33 times 67 over 100, which is not right. You have to write this. So that's what we're going to have to write. And that would become your standard error. So instead of writing like basically that, we have like 0.33 times 0.67 divided by 100. So they're different numbers, basically. And that's what you have for standard error. And now to find your confidence interval, because it's going to be between two numbers, like it's going to be like, let's say it's between like 0.2 and 0.5. So you're like 95% confident that like the freshmen's the amount of freshmen, the proportions of freshmen in the class in that school is between 20% and 50%. Because you're not exactly sure how much there are, they're just between like some numbers. So basically, you calculate it. The number is the lower number is just the mean minus the z score, which you calculate from your mechanics. So you use it here times times your standard error. And then to get the upper limit, which is the upper like percentage, would just be mean plus the z-score. Oops, sorry. Score times your standard error, basically. And then once you write this for your when you calculate these values, you're gonna put it in like brackets. So let's say it was like 0.1 and 0.5. And you say it's between these numbers. Level. Okay. I mean interval. Interval. Sorry about that. And then you basically just write I'm something percent confident that the true proportion, so like the actual proportion, so it's the true proportion, like the actual p, it of whatever you have to write, like of basically you have to put this in context. So I'm 95%, everything you have to write in context always all the time. So you say I'm 95%, I'm something percent confident. Let's say I'm 95% confident that the true proportion of the true proportion of freshmen in that high school is within the interval, like the interval, and then you write your interval. So your interval is like, let's say 0.1 to like 0.5. It's within the interval 0.1 to 0.5, and that's basically what you write. You always have to write this down like actually. So if you copy the statement, you're generally correct. So that's basically for confidence intervals. Now let's actually work on an example. So let's say there's a marble company, right? Something with marbles. The marble company claims that 25 of their percent 25 20% of their marbles they make are red. Okay? And when you open your bag of 100 marbles, right? 100 marbles, you find out that 30 are red. So basically, your question is asking: is the company underestimating the amount of red marbles? Because you're saying that like there's 30 reds, which is greater than 20, because 30 divided by 100 is 30%. So it's greater than 20%. So are they underestimating the amount of red marbles? So basically, you have to cut your condition. You say it's random, right? So you say it's random and you write it down like word for word. I'm not gonna write it again, but basically just say you have to write it down at least the word random. You say the bag is random, so the marbles put into the bag are basically random, and then you have independence, right? Uh, Okay, independence, which states like just because you put one red marble into the bag doesn't mean you're gonna put another red marble into the bag. So basically something like that. So the color of the marbles in the bag are independent of each other. And then you have 10% condition, okay, which states that the bag of 100 marbles is less than all the marbles ever made by that company. You know, because they're claiming that all their marbles is 20% red. Oh, sorry, I don't know why I deleted that 10% condition. So you write n is less than 10%. Okay, because your n is 100. So and then you write your sample size, which you do all the math in. So your percentage for PO is 20, right? So your 20 times your N, which is 100, is 20% times N is 20. So your NPO is greater than 10 because NPO is equal to 20. And then the QO is just 1 minus that 20%, so it's 80%. So 80% times 100 is 80, which is also greater than equal to 10. So you check all your conditions and you say it's right. So and then you write your transition statement. Since the conditions are met, I'm sorry about the bad handwriting, are met, I can construct a one proportion z-test. These are just stat tests, which also call sampling distributions. One or one, doesn't matter. Basically, you just gotta write it down because you satisfy all the conditions. And then you write your test, which is basically HO. So your P, the true proportion of the red marbles, let's say it's equal to the company, which is equal to 0.3. I mean 0.2. The company claims that it's 20% is red. And the alternative hypothesis will be like, since the question is asking you, is the company underestimating it? That means your alternative would be like if the actual number is actually greater than 0.2, because the company is underestimating. So you think that like it's greater than 0.2. That's your null hypothesis and your alternative hypothesis. And now you have to define your variables. Actually, I'm just gonna write this smaller, because I'm gonna put this onto like basically this entire thing. HO. So P is equal to 0.2, and HA, where P is greater than 0.2. You always have to write these. Just put like colons. And then you define your variables, which basically states PO, which is basically the proportion of red marbles claimed by the company. And then you have P hat, which is the proportion of red marbles in your sample. Oh, sorry. In your sample. And then N is your sample, your 100 marble sample, bag sample size. Okay? So basically that's what you write. You can always, if you also want to do, you can also just give them the number like equals to 100, where P is equal to, your P hat is equal to 33 over 100. I mean 30 over 100. Sorry about that. Because you found 30 red. And then you also just write your Q hat if you want, which is the proportion of red, proportion of marbles that are not red in your sample. So it's equal to 70 over 100. You can also write that down if you want. So you define your variables. Now let's move on to the mechanics. So your mean, which I usually just write as M, is equal to your PO. So your mean is 0.2. And your standard deviation is equal to the square root of PO, which is 0.2, times QO, which is 1 minus 0.2, which is 0.8, divided by your sample size, which is 100. So using your calculator, you have square root of 0.2 times 0.8 divided by 100, and you get 0.04. Okay? Let me just double check if that's true. 0.2 times 0.8 divided by 100, square root. Oops, sorry. Okay, yeah, 0.04. And then now you have to find your z-score, which I just write as z mostly. Z is equal to your p hat, which is 0.3, minus your mean, which is 0.2, which is basically just your PO, divided by your standard deviation, which is 0.04. So it's 0.3 minus 0.2 divided by 0.04, which is equal to 2.5. Okay? And now you have to write down your alpha level. So you could just write this down on the side because it's not really part of your calculations. So let's say you write it here and say your alpha level is 0.5%. So it's 0.05. So it's 5%. So if it's less than 5%, like your p-value, then then it's basically wrong. So then using your calculator, which I use a TI Inspire, CX, or CAS, they basically do the exact same thing. You basically, in your calculator section, right, you just go on the calculate, you press menu, you press, yeah, you could either press probability or distribution, it doesn't really matter. You go onto the section called distribution, and then you go to normal CDF, right? And then, if, since we're saying it's greater than, if they're gonna have a lower bound or upper bound, something with the U means mean. That's what the U means. U right here equals mean, and that kind of like O kind of thing with this is standard deviation basically. So basically, if the lower bound is basically just a really big number, like if you want to find something greater than, like if you have a picture like this, right, and you want this amount. The higher you just want a bigger amount, like you want a really big amount, so you put 9E999, or like just some kind of really big number. It doesn't have to be this number, because this number is just a really big number. So they want to calculate like a really big number, and then like if you want to calculate smaller, right? You put you put 9E999 in the upper bound, and if you want to find a lower number, like you want to find this number, you put negative 9E999 in the lower bound, and then you type for the upper bound, right? So for in this case, we're gonna be talking about the Riemann or null hypothesis is the p-value is greater than 0.2, right? So you're gonna have to you want to have a number that's greater than than basically that amount. So we have something right here. Let's draw a picture. This is it's sometimes easier to draw a picture and then you do the your p-value first. So your mean is 0.2. Your standard deviation is 0.04, and your p hat is 0.3. So somewhere right here. So if you kind of think about it, you have one standard deviation, which is just 0.4 plus 0.04 plus 0.2, which is 0.24. Two standard deviations is 0.28, and then three standard deviations is 0.32, which is just a little less than it. So this one is like really small. So it's like right here. So this already seems like it's unusual, but you might want to check it. So you want to count here. So the z-score right here is like basically 2.5, which is the z-score. But basically, all you have to draw is basically write the 0.4 on top, 0.04 as your standard deviation, 0.2 as your mean, and 0.3 as your p hat, and you have to color this in basically, and that's your area. And basically for Inspire, you basically just leave the negative 9E999. I mean, not negative 9E. For the lower bound, you're gonna have 0.03 because you want to be above it. So anything that's positive, because you want to be greater. And then like you want a really big number, because as you see right here in the graph, you could get like a really big number because this never crosses the 0. This just keeps going on infinitely, but it gives like really small areas, so it kind of does nothing after a while. So you just put like a really big number. Usually just write 9E999. And then your mean, which is 0.2, and your standard deviation, which is 0.04. And you get a p-value, which is equal to 0.000621. You could probably stop at 0.06 or 0.062. I usually just like to write at least 3 significant figures to like the decimal. So if there's 2 zeros, I'm just gonna ignore the zeros and then I'm gonna write the 3 numbers. And you basically just always round up. Just do your rounding scale. Or like if you have like if it's greater if it's 5 or greater, you just round up. It's 4 or lower, then round down. Like just use the normal math ways. And then you have a p-value of 0.062, right? And you drew your picture and you did your your mechanics. So we're gonna now write our conclusion. So based. So we have based on the p-value of 0.00621, which is less than the alpha level of 0.05, I re I reject the null hypothesis. Okay, and then you basically write the alternative to hypothesis. I don't know why I wrote so big. Uh, there is evidence to suggest the amount. I'm just gonna say the rest of when I'm running out of space. There is evidence to suggest the amount of red marbles made by the company. The total amount of red marbles made by the company is greater than 20%. Because that's that's your alternative hypothesis. Where P, which is the actual amount for the red made by the company, is greater than 0.2. So it's greater than 20%. So you have to say that the um the null hypothesis is wrong and the alternative hypothesis is true. Okay? So you always have to write it in context. Always write it in context. And then if they ask you to follow up with a confidence interval, okay? So your mean, this right now is your p hat. So your p hat would just be 0.3, and your standard error is equal to the square root of 0.3, like it's p hat times q hat, which is 0.7, divided by 100, because that's what's your sample. Okay. So you have square root 0.3 times 0.7 divided by 100, which is, you could round this up and say this is approximately equal to 0.0458. I usually just write 3 decimal places. And then you basically calculate for the thing. So now you have the mean plus or minus the z-score. We're not going to use the previous z-score. Sorry if I said it was the previous z-score. It's not the previous z-score. It's the z-score times the standard error. So the z-score that you're going to find is like what level of confidence you want. You want 95% confidence, a 99, a 99.5, you know? So basically, what you do is that you kind of go into your calculator, right? And then you go to like probability or statistics, you know, I don't care. It's basically the same thing. You just go to distribution, right? And this time you're going to click inverse norm. So the area that you want to have is this is going to be a little tricky. It's a little different. You can't just write 95% if you want 95% confidence. What you have to do is that it kind of does something like this, right? So when they asking for the area for the calculator, what it does is that it's, let's say you want a 95% area, right? You have to, they calculate the area like this. So it calculate this is the 95, right? When this is not true, when what you want is the 95% is this amount right here. But they add like right here when you're not. So basically when you have to have the 95, since it's symmetric, you just have to do a little bit of math. So usually when they do, let's say you want to have a 95% confidence, like your 95% confidence is between this interval, then right? Then basically, since it's symmetric at both sides, right? So when you're having a, so what they're doing is that you want to have a 95, like right here, right? So this portion is 5%, and this portion, I mean not 5%. Since it's symmetric here and here, right? This side and this side is symmetric, then basically this and this has to be equal. So if this is 95, it's just 100 minus 95 is 5. So this is 2.5%, and this is 2.5. Because 2.5 plus 2.5 is 5, plus that 95 is 100. So this is 2.5. So then you have that 2.5, so you have to find this area over here, which is just this area right here added together. So it's 2.5 plus 95, which is 97.5%. So in your calculator, you write 97.5%. So you write the area is 0.975, and you're just gonna leave the mean as 0 and the standard deviation is 0, and then you're gonna get a z-score of 0.96. You know, and then basically you're just gonna do the math on this. So you have point mean, which is 0.3, plus or minus 0.96 with a 95% confidence, times the standard error, which is 0.0458. So you have 1.96 times 0.0458, and then you have 0.3 added to that number, and 0.3 minus that number. And then you basically just round. And you have, it's between 0.2, when you have 0.3 minus 1.9 times 0.0458, you have 0.21, and you have when you have 0.3 plus 1.9 times 0.0458, you have 0.39, and that's your the value. So what you write is basically, I am 95% confident that the true proportion of red marbles created by this company, be specific as possible because you want to write everything in context, is within the interval of red marbles in that company is within the interval 0.21 to 0.39. It's 21% to 39%. So um so that's basically how you find with your confidence interval. Because they claimed it was 20. Because that's why you always use the confidence interval to determine. You could kind of use the confidence interval to determine if they're underestimating. Because they claimed it's 20%, and 20% is not in here. It's outside because it's 0.21 to 0.39. Right? So this 0.2 is outside, which what they claim is 0.2. It's outside the confidence interval. So you're not. So it doesn't seem like it's right, even though it's like 0.01 away. But it's, if you have a confidence interval of 95. If you have a confidence interval of 99, maybe you'll have 0.2. So that's why like if you increase the confidence interval, it gets, you could like include it basically everything. And that's how like people are coming up with these statistics. Like there's like 95%, 99, 80 or something. But basically it's just a range of numbers of where you think it is. Another way you could do like these this one proportion z model without actually doing the math is that if you have an nth bar, which I'm using right now, you could just go to your calculator, go to statistics, and then press then go all the way down to stat test, and then you're gonna basically just choose one port z test, which is number 5. Then from that menu, you come out with a PO, a success, a N, and an alternative hypothesis. Our PO, we already said it was what is claimed to be true by the company, so it's in our case, this one is 0.2. The number of successes, we said it was 30 reds out of 100, so we have 30. The N is the amount, which is 100. And then we just have to write our alternative hypothesis, which is greater than PO. So it's the first one. And then you press OK, and then you basically get everything, where the z-score is 2.5, the p-value is 0.0621, and then the p is 0.3, and the n is 100, and you basically do something like that. For the confidence interval, you basically go back to the calculator, go to stats again, go to the sixth one, which is confidence interval, then you choose one port z interval. Number of successes was 30, n is 100, and this time you don't have to do all the math to find the area. Whatever confidence interval you want, you just want. So if you have 95%, just put 0.95, and then you press OK. And then your lower interval is 0.21, and your upper interval is 0.39, right? And you get your mean, and you get your n. in your P. So basically, it's just that easy. That's all you have to technically do. Um, That's so if you don't want to like do any of the like math, like if you're ever doing like the AP exams, all you technically have to do is just go to like if you have an Inspire, just go to your calculator, go to like the statistics, and then like click the confidence intervals and the hypothesis tests, which whenever you need, and you basically just plug in all the variables and then you get it right basically. And you can just write them all down, define it, and that's all you have to do. Because if you're ever on a time crunch, basically you don't want to do like a bunch of the math. Basically, just write all the math down, but you don't have to do like all the setups. You just say like the p-value is equal to this, the z-score is equal to this without showing a bunch of the work. So that would be fine too. Well, that basically covers everything about z models and z models one proportion, z test, and its confidence interval. Thanks for watching, and I'll see you at the next math record.